In the previous videos, we discussed the types of metal and polymer manufacturing. In this video, we will cover ceramics and composites manufacturing. Ceramics are materials that are non-metallic and inorganic. They are typically hard, chemically non-reactive, wear-resistant, and heat-resistant after formation, and they can be formed with heat. Despite their high mechanical strength, ceramics are usually very brittle. They are also good insulators and are unreactive with other chemicals. Some examples of ceramics include glass, cement, pottery, and bricks or tile. Ceramics manufacturing types include pressing, injection molding, extrusion, and casting. Each of these methods creates a green body. A green body takes the shape of the final part, but it must be heat treated to dry and harden into the final part. Powder pressing is a process in which ceramic powder is placed into a die cavity, and a mechanical or hydraulic press will move downward, compacting the powder. This process is repeated several times until a green body is produced. Injection molding is a process in which ceramic powder is injected into a die cavity. Here, the ceramic powder will bind to create a green part that will then be ejected by the machine. Ceramic extrusion is a process used to create rods, tubes, or pipes. Ceramic paste is placed inside the machine, and an extrusion ram forces the material through a die, which produces long tubes of material. Casting is a process in which ceramic powder mixed with water is poured into a plaster mold. The plaster soaks up the moisture from the ceramic mixture, consolidating the part. Next, excess materials can be poured out in order to create a hollow part. Remember, the ceramic parts produced by these methods of manufacturing must undergo a heat treatment to produce a finished part. Ceramics are further categorized by their end use or application. Whiteware ceramics are the types of ceramics that we are most familiar with. These include stoneware, dinnerware, and porcelains like sinks or dental crowns. Refractory ceramics include ceramics that can withstand incredibly high temperatures. These are made of substances like silicon carbide or zirconia. Some examples of refractory ceramic applications include heat shields used in the aerospace industry, ceramic crucibles used to melt metals or other ceramics, as well as fire clay kilns or furnaces. Engineering ceramics are also called pure or fine ceramics and include man-made ceramics that have enhanced properties. Because engineering ceramics are superior in heat resistance and strength, they are often used as cutting or machining tools. These cutting tools do not retain heat, allowing them to work at high speeds. They are used to cut materials like cast iron and nickel-based materials, which are often difficult to machine using other methods. Composites are a combination of two or more materials with different properties. The combination of these properties help to strengthen the material. Fiberglass is one example of a composite material. Fiberglass is a type of plastic reinforced with glass fibers, which makes it lightweight, strong, and a good electrical and thermal insulator. Carbon fiber polymers like polyester, nylon, and vinyl are polymers reinforced with carbon atoms to make the material resistant to corrosion, in addition to strengthening the material. Ceramic matrix composites are made of two or more different ceramics, producing a material with high strength, even when temperatures are elevated. Like the other materials we have discussed, composites can be manufactured by CNC machining. Some additional manufacturing types for composites include contact molding, vacuum bagging, and resin transfer molding. Contact molding is a simple and popular manufacturing type for composite materials. To understand this process, we can think about the steps of installing wallpaper in your home. First, a primer or light adhesive is applied to the walls. Then the paper is carefully spread out onto the wall. And finally, an adhesive is brushed onto the paper to adhere it to the wall and also to harden the paper. In the first step of contact molding, a gel coat is spread over a tool or mold. This gel coat will be the outer surface of your final part, so the color and finish must be chosen accordingly. After 2 coats of this gel are fully cured, a layer of the reinforcing fiber, usually glass fiber, is laid down across the mold. Next, resin is poured into the mold and spread around with a roller. Once this layer thickens or gels, The process is repeated layer by layer until the desired thickness is achieved. The final product may take a few days to cure before it is ready to be removed from the mold. After removal, the final part may require some post-processing, like sanding or polishing. Due to possible inconsistencies in layer thickness, this method of manufacturing is not ideal for small, intricate parts. In fact, it is most often used for extra-large parts, like the body of a boat. This manual process is time-consuming, but it is ideal for producing single or low-volume parts. The vacuum bagging process begins similarly to the contact molding process. First, a sheet of the reinforcing material, like carbon fiber or Kevlar, is placed into a mold and adhered with resin. This process is repeated for a few layers until the desired thickness is achieved. Next, a layer of peel ply and a layer of breather felt are also applied with the resin. The peel ply helps us easily remove the mold when it is cured and ready, and the breather felt helps with airflow during the vacuuming process. Finally, the mold is placed into a vacuum bag where all the air is sucked out, creating enough pressure to conform the material to the mold. Due to the uniform pressure applied to this material, parts manufactured by this process are typically very strong and have a very good surface finish. This method can be used to manufacture extremely large parts, like wind turbine blades. Resin transfer molding begins by inserting reinforcing fiber into the cavity of a mold. The mold is clamped shut and resin is pumped into the cavity, wetting all of the fibers. Under high temperature and medium-high pressure, the resin will cure. Then the mold can be opened and the part can be removed. This process is quick compared to others, and smaller parts can be produced in only a few minutes. This manufacturing type is ideal to create a medium amount of parts, from about 1,000 to 10,000 parts. It is not ideal for low volume production because the cost of the metal molds can be quite expensive. If you take a look around a hospital, you will see that you are surrounded by composites. From the components of X-ray and MRI machines, to mammography plates, to wheelchair frames, composites are essential in the medical field. Composite materials are ideal because they allow us to combine the best features of different materials. For example, a carbon fiber prosthetic offers the high strength of a material, but it is very lightweight like a polymer or ceramic, and also offers an aesthetically pleasing appearance. Some polymer composites may be permanent solutions to replacing an entire bone due to their high strength and biocompatibility. Other polymer composites may be used as bone supports to aid in bone regrowth, and over time they will be safely absorbed into the body, eliminating the need for invasive removal of the supports. Since there are countless options for composites, there are a few things to consider that may help you understand the type of composite material you may need for your product. You might want to ask, does this material need to be biocompatible or just skin safe? Is the product reusable or disposable? Does it need to be heat resistant to withstand steam sterilization? Should it be stiff or flexible? Questions like these will help you understand the type of material required for your product.